Roberto Rosario. We talk about Dockerizing Django projects. Thank you.
Well, grazie mille per essere qui. Io sono Roberto Rosario, io sono di Puerto Rico. E questo per me è un grande piacere per parlare a tutti oggi. La comunità di Python d'Italia sta in un posto molto speciale nel mio cuore. Grazie. Well, I'm Roberto. You can find me, and I was very lucky to find my name online available, so I grabbed that, and you can find it. I will put all the material of the presentation there. I apologize. I'm having some technical problems with the internet and with my travel arrangements, so I hope the presentation will work until the end. So. I work for Cryptico. Cryptico is a cryptographic API design company. Also, we do a lot of big data for the government, and we use a lot of Docker and Django for deployments. My presentation seems to have a mind of its own. I also work for Mayan EDMS, which is a paperless, an open source paperless solution. And Paperless Inc., which is the enterprise counterpart of that project. And they are done in Django, and they are deployed via Docker, which is where a lot of the pains and solutions from this talk came. So what is Docker? And why is it important for us in Django? Well, in their own words, it is an integrated technology suite that enables development and IT operations for teams to build, ship, and run distributed applications anywhere. What does that mean? Well, just containers. That's it. That's all they do. So what are containers? They are more or less like virtualization, but not exactly. So they will probably be blaming me now because I'm saying stuff that they say is not true. Well, it is true. It is virtualization. What we are trying to do is take the hardware out of the equation and make the application the most important part of our stack. Docker promises be able to, you can deploy your applications everywhere because now the hardware is not as relevant as before. Now the application is basically the center stage of your stack of deployment. Docker promises easy scalability because we are now doing lightweight virtualization. We are not emulating hardware. We are not emulating a lot of platform. So we can spin up multiple copies of our project and deal with scalability. Basically, in just seconds, we can react to an increase of use of our application, and at the same time we can also scale down very fast when that usage has finished, and we don't have to pay extra if we are deploying in the cloud or in Google or another service provider if you are not using your own. Docker now also even has auto scaling. We can put certain key performance indicators, watchers. It can be CPU load, it can be traffic, and Docker will react to that and increase a new front-end copy, a new database, a new worker, more load balancers. Well, I'm sure that if you like Django, you have had to deploy Django a lot of times. So what's usually the way you do? You take your cold metal server, and you put there your database, your broker, you put Redis, you put your front end, you put workers. So that's great. You just deployed Django, your Django project. Congratulations. 2 weeks later, now you have 4 times your users. So what do? Easy. You just get another server, and you know another database, another broker, another Redis. another load balancer, and after a while you end up with a farm of servers which you have no idea which one is doing what, which is doing application serving, database serving, and you end up with a farm of servers. So when virtualization started to become mainstream, everybody was doing virtual environments, virtual VMware, VirtualBox. So we started doing virtualization, where we started making the same mistakes. Because it is so easy to spin up a virtual machine, we started doing the same thing. In just one virtual machine, we put database, front end, workers, and brokers. At which time we just end up replicating the same problem. What Docker does is that it allows you to split your architecture into smaller units, what Docker call containers. A container is just a very thin operating system and your application. That's it. And because its way of virtualizing your application is so thin, it has very little overhead on the host operating system, unlike VMware, which basically emulates hardware. It's emulating a whole computer and software. Even though modern CPUs have virtualization capabilities and can execute code outside the context, there's still virtualization is still very, very heavyweight. What Docker does is a Linux container, which basically is a jailed application. It is not true virtualization, because the CPU is still running the code in the same context of the host operating system, but it's doing CPU groups, so it can actually do CPU execution quotas. It can do memory quotas, and it can use the host operating system using a layer a system of called UnionFS, so that only changes are written to the file system layer. So you're saving in CPU time, you're saving memory, and you're saving storage, because you don't have to provision an entire disk for each virtual machine or for each container. So what you do in Docker is you create one container for each part of your stack. One container for database, one for front end, one for back end, one for your brokers if you're doing background tasks. And what you do is you just spin up, because they are so cheap in terms of memory and execution and storage. You just bring up new containers when you need them, and you just destroy them very easily when you don't need them. So basically, your whole infrastructure becomes very elastic, horizontally and vertically. You can have more platforms, and you can also increase the capability of those platform services at will. So how do you convert a Django project to work as Docker? It is not so straightforward, because Django needs to be initialized every time you install it. You have to migrate your databases. You have to collect your static files. It doesn't lend so for an easy one-to-one translation into Docker. Docker works with images. An image is basically a blueprint. A blueprint of how the Docker container of database is going to be built, how it's going to be instantiated, how your front end is going to be instantiated, and your workers. So before starting to use Docker, you have to create the blueprint for your containers, what requirements they will have, what ports they will expose. From each blueprint, from each image, what is called in Docker, you can create several containers using the same image. So in essence, if you think like Python, the image is like a class, and your container are instances. It's an overly simplistic view, which the people from operations don't like, but we are programmers, so this is how I came about it. Once you have your images defined, which you can publish them online using Docker Hub, or you can have your own private registries in your teamwork of Docker images. So your developers can continue working and creating new versions of the images of your products, and your operations team can just roll out new versions of your application versions. This is what a Docker file looks like. This is the blueprint that will tell Docker, okay, this is how I want you to build an image. It can be deployed 1,000 times. And this is called a Docker file. It has a very simplistic, on-purpose syntax. It's basically a batch file with a few other things. And you tell it from which base image it will build this image. So you don't have to build your image from scratch. You can also reuse. And a lot of companies like Ubuntu, our Postgres, and Redis are publishing their official container images for their products. So you don't have to learn how to containerize Postgres. They already done it for you. So it might sound like overhead doing an entire container just for an application, but it is lightweight. It does very nice. Docker does what it does very nicely. Because the operating system, like I said, works on layers. You take the base disk image from Ubuntu, for example, and it will create just changes for your application and still store the original file system layer. It's called a layered file system driver. It works like differential backups. You have one initial snapshot, and then it just records the changes that your application does to that file system. So even though you have to download an entire operating system, which in Ubuntu can just be shrink down like 600 megabytes, you only do that once. Even if you deploy that image 10 times, it will only download and just use on the system 600 megabytes. And for each image, it will only consume on disk the difference for each container. So even after 10 containers, you might just be using 700 megabytes of disk out of the 100 that the initial image costs. So it's very, very economical. This is just what I explained. You can take the base image from Ubuntu. They release a lot of official images for everything from i386 to 64-bit to AMD to to ARM, for example. They have that to define your specific needs for your application, and you can build your own image using the base image from Ubuntu. So in a sense, Ubuntu's image is a base class, and your image is a subclass of Ubuntu's image. Again, an oversimplification. Operations people hate that, but that's, if you think like a software development, that's how you can understand it very easily. The problem with Docker is Docker was not designed for stuff like Django. Docker was designed for stuff that is self-contained, like, for example, Go language, where you can compile your application into just one executable. With Django, it doesn't work. It doesn't play very well. So in the course of Dockerizing our software, we've come up with a few approaches. The first one is monolithic. It means you include everything that is needed for your application to work in just one container. You include your application, the workers, in case you're doing background tasks, which we do a lot, and the Nginx web server in just a single container. This way, when it is deployed, it just exports one port, the HTTP port, which then we can connect with our load balancer, and we can scale very easily. It has advantages and has some disadvantages. When we deploy it, it is very easy to deploy. We just deploy our database image, the broker image, and then our monolithic. With just 3 commands, I can deploy a clean instance for one client, for example. The bad thing is, it's a very big image because it has Nginx, it has Django front end, and my Django backend stuff. It's not very good for scaling because if I deploy multiple copies of this image, I will have many Nginx, I will have many duplicates of my stack. And it basically repeats a lot of the problems we have when we do virtual machines with VMware. The good thing is that it's very easy to maintain, it's very low barrier. So we tend to use this for the open source version of our products so that new users can just start trying our product with the minimal amount of downloads and minimal amount of commands. Another approach is to split your architecture in different containers. For example, you can take the front-end part of your system into one container and the back-end, the celery part, the background tasks, the cron jobs into another container. This way, if what you are having is front-end scalability problems, for example, too many requests per second, you can just put up another front-end Docker container, another instance with your load balancer, but you don't touch the backend because the backend is okay. If, on the contrary, you're having too many background tasks are overloading your broker, you just scale your backend side of your application. So basically, a split is just splitting what the users see and what operations teams see into different collision zones, basically. Again, it has advantage and disadvantage because no one single approach is the best when Django. And this one is most suited for production because you can now control the scalability of different parts of your stack independently. It is not so good for making your software known to the general public because now they have to download at least 2 new images and they have to connect them when they deploy them. Another big disadvantage of this approach is if you have your 2 containers defined in a single Git repository, Docker would only be able to generate 1. Docker right now has a disadvantage that it can only generate 1 Docker image per repository. So with this approach, you will actually have to split the development of your app into 2 different Git repositories so that Docker can generate the container image from each one. Another approach is the mix approach, which is I create just 1 single image, but I make it that it can react to environment variables. For example, and I can pass a setting, okay, you are an image that can do front end and back end. But for this instance, I want you to work as front end. So it's just 1 single code base that can react and can generate 2 different classes of instances. And the way you do this is in your configuration scripts, in your Docker files, and in your run bash script, you put your code to look for whatever variable you call, and it will execute different code depending on the value of that variable. So basically, you can tune it to do different kind of works. Again, advantages and disadvantages, and the bigger one is that this image is going to be very big and you will have stuff that you might not use. For example, if you are deploying this image as a backend, it will still have Nginx and a lot of front-end stuff installed in it. So there will be a little bit of space waste. The good thing is that with this image, you can reuse all your configuration file templates in just 1 Git repository. You don't have to split your development with this approach. There's another approach which it's called the lean approach, which is basically you split your Django project into as many little pieces as possible. That means putting your front-end work and not even including Nginx in it. But that means that you are going to have to deploy a container of Nginx for each copy of your front-end containers. If you're using MicroWSG in HTTP mode, it's not going to be a problem because you just connect your containers, your Nginx container, to your Django containers. We know that if you want to use as much CPU power for your app, this is not the best approach. The best approach is using Linux socket, and in that way, in that method, you cannot connect them because basically they have separate file system, and you will not be able to work with it. So it works in some instances and in others. The good thing about this one is that you don't have to worry about Nginx. You can use their official container. But for every instance of your front-end code, you're going to need one Nginx instance. So you're going to have Nginx 1, Django 1, Nginx 2, Django 2, Nginx 3, Django 3. If you turn off one of your Django front-end code, you have to turn off the corresponding Nginx container, and that can become quite a hassle. The other problem is that you're going to have the Nginx container is configured via a command line. So you're going to have to include configuration files that are called every time the container spins up, which is, in terms of configuration management, it can be quite a pain. And one last approach, we don't do this, but I've seen it done. Call it the kitchen sink. We saw one, the University of Montreal does this. They just take one image that has everything. It has Django, it has Maya, the project, the entire project. It includes Postgres, Redis, RabbitMQ, everything in just one gigantic 3 gigabyte image. Don't try it, because it's just a humongous download. It doesn't scale. You have to maintain things you don't own, like Postgres. It just has one use case. It is when you have to do like a educational version of the software, so that students don't have to think about anything about deployment. They just take the image the professor gives them, and they just instantiate that image for their use, and they destroy it. But don't ever use it on production. I really mean it. Ever, never. Because it is so big, it's going to kill your server performance. It's going to destroy your throughput. No, your operation people will actually hate you very much. One thing that Django does, that Docker kind of doesn't have a system for it, is post-initialization actions. Docker expects your software to be ready when the image is instantiated. Django doesn't work like that. We have to deploy Django. We have to run our migrations, create a superadmin. We have to collect our static images, and we have to do other stuff that our application might need. So Docker has something that's called exec, where you can actually go inside the instances of your images, and you can execute code. Don't use it, please, because Docker expects your image to be ready at the moment you deploy it. So what you can do is this is kind of a hack, where you can, in the entry points of your image, you can collect and you can do all the necessary initialization for your project. You can, and what you do is you call your initialization code and you make it a little bit smart, and it will, if it detects it already has been initialized, it will ignore that command. Don't make it fail, just ignore it silently. So every time your application is deployed, it will try to initialize. If it's already initialized, it's no problem. It will not raise an error. That way, even if it is the first copy or the 10th copy, you can just deploy it with just one command, which is the Docker run. And you collect static images. You do everything in the run command. One of the other biggest problems with Docker right now is service synchronization. If I deploy images, I don't know when they will be available. You don't know when the image has finished initializing. So you're deploying your stack, you deploy the database, you deploy the broker, and you deploy your app, and all of a sudden you have an error. Why? I just deployed the database. It's supposed to be there. And the problem is you have no idea of knowing when the database has been available. So you have to put your wait. You have to let your images, your Django images, wait. Docker doesn't provide a service for this. So one of the most popular approaches is to install NC, and you just pull, you ping, and you bother that port until it doesn't reach an error. And you assume that the database has been brought up. It's a very ugly approach. Docker refuses to do an official service for this. That's the way things are going right now. Why? Because my application configuration files are not the place for me to be watching another service. That's the job of Docker, not mine. And if you have many services, you just have to start copying and pasting this code all over your configuration files, first waiting for the database, then waiting for Rabbit to be available. If you use another Redis, you have to wait for Redis then. And if you are not careful, you're going to end up with 10 blocks of code just waiting for different services to be brought up. This doesn't always work, because just because a port is available doesn't mean that that service is available. Many of these services have APIs, which might provide an endpoint that they will tell you when they are available. With this approach, you cannot do that. You can only just check a port on another system. That doesn't have too much context. Plus, NC is not an universal install. Many versions of Linux don't include NC. So what options do we have? A few people have come up with several approaches. One is very interesting. It's an entire Docker image designed just to wait for another service. And you just connect the containers and you tell it, you don't have to tell it the port, it automatically knows the port that is being exposed, and it will pull and wait for that service to be ready, and then it will launch your container. It sounds interesting until you have a closer look, and it's actually doing the same thing. So it's just an entire container for NC. Yeah. Just because it is clever, it doesn't mean it's the right solution. So how do you fix this? What's the problem? Docker is not giving you something that you need. It's Docker's fault. It's Docker's responsibility to provide you this. Sadly, issues open with this topic automatically has been closed. There has been several attempts, and no, they're very reluctant to incorporate that in Docker. Kubernetes, on the other hand, listened to the community, and they did include a very, very nice way of you to know, your application to know if your service that your application needs, it's available, and if it has died, so that it can initiate that container if it has died. So you know if it's ready, and if it was ready and died, and you can check ports, and you can check path, and you can have initial delays for start checking that service, and you can have the timeouts. For example, if this port and this path stop responding after 1 second, I know that this container has died. And that approach is very nice. It has everything that it needs. That you basically win the support. Docker upstream, now that they see the approach, they, oh, okay, this is the way to go. So they open an issue, and they are trying now to emulate what Kubernetes did, which I think is the best approach. The other thing is templating. Your configuration files are static in an image. So you need a way to change, for example, paths, to change any kind of stuff cannot be always static. And Kubernetes, Docker images are configured using environment variables. So why not configure our images, our configuration files using environment variables? Well, easy. Not all the software used in our applications that supports reading environment variables. So again, this is another problem that Docker needs to address. How can I do variable substitution in my configuration files? Again, they have closed basically every issue that it's happened in this. And this kills me. This is basically, yes, we know this, but it will be fixed by someone else. And I've seen that many times, and it's also very frustrating. I don't like hearing that. If I get here, please help me. Don't send me somewhere else coming in for food. The options, well, there's a few people that are handling this. This is a very nice approach. It's not an entire Docker container. It's just a Go application that's compiled that can do environment variable substitution in your configuration files. And then there's this guy who just managed to nail every point. It's called Dockerize. If you're going to do Django Dockerization, use this. Don't use anything else because it solves every problem. It's just a Golang that can do templating, can help you wait for other services, and it can help you export the logs of your containers so that you can read your logs outside Docker without having to execute code inside Docker. I don't think we have time for the demo, so lessons learned. Docker is great. Docker is awesome. But it has a kind of approach to dealing with things that it will have you hunting for solutions, which usually are not the best ones, and means that so when dealing with Docker, there are no easy solutions. That you have to be willing to go outside your comfort zone to try new things, and they might be just crazy enough to work, so give them a try. Thank you.
Thank you, Rosario. We have 5 minutes for answer questions. Any question? Okay.
Hi. Have you ever deployed any application on, for example, Google Container Engine or another type of cloud services, cloud system as a services?
Yes. Right now, we are using DigitalOcean for testing and internal development, and Google Cloud Engine for production. And Google has a managed version of Kubernetes, and it's very good. It's very expensive, but if you don't have a very big operations team, it's a very nice option. And you can also, because Kubernetes is open source, you can also deploy your own Kubernetes. I don't recommend it because keeping Kubernetes up to date, development is happening right now very fast in Kubernetes. So my approach would be go with Google. I don't work for Google. They don't pay me, but it's the best commercial version of Dockerization services right now.
Hi, Roberto.
Hey, Jacopo.
So with Docker, you spin up tens of containers, and then you have tens of things, and you must know how they are behaving, if they are dying or whatever. So you just, in a sense, to me, you just move the problem in another zone. So there are tools to handle this pain of knowing about these tens of machines running around.
Yes, sadly, they're not in Docker. Kubernetes does that very nicely. Kubernetes has a lot of metadata for every instance that you have in production. You can put labels on them so that you can then tell the networking layer, every container with this label, please connect it to the load balancer, or it will run in this sub-network. And you have what they call the liveliness test, where you can have a log of how each container is responding. And now they're adding assistants where you can tell it, if this container doesn't answer this ping or this heartbeat in 2 seconds, kill it and just spin another one and connect it to everything in production. Docker was a very nice start, and Kubernetes is picking up where it kind of left off. They went up to a very big start, but a lot of services are missing or are not implemented in the best way. So if you're not careful, what the scenario you just explained will happen. You will have just a jungle of unexplained containers that are running and you don't know what they do.
Another question?
Okay, so I don't have probably too much experience with Docker, but doesn't, for example, Docker Swarm solve this problem?
If you use Docker Swarm, you have another problem. They are now addressing it is networking. You can have 2 Docker hosts, and your container from each host might not talk to each other. So if you deploy your database in one host and your application in another, they might not talk. Kubernetes has solved the networking approach very good. Swarm doesn't have tests to see if a container has died or is alive. It does have some service synchronization support, but it's very vague and it's not even compatible with Docker vanilla. The environment variables are different, so you have to actually modify a little bit of your images if you are going to run them in Docker Swarm or you're going to use Docker Machine to spin up your host.
So basically it's like too early for Docker Swarm to use it really.
Yes, right. Actually, just until 2 months ago, there was a big warning that said this is not for production.
Okay.
It just came out of beta 2 months ago. So it is a. They're moving into the right direction now, but already all the solutions have moved ahead.
Yeah, so about the waiting for synchronization, it's a good idea to look at the logs. We had the same problem. You just say Docker logs and wait for something like it has started, because sometimes say you are waiting for synchronization in the host, it's not, the port may not even be exposed to the host.
Yes.
And I wanted your opinion on about, like, you talked about like big containers. Do you build everything in the container? Do you build like say requirements which have C dependencies inside the container, or do you only build whatever you need if you have such a big container?
Well, our official approach is the split approach, which means, yes, we do include a lot of libraries. We do all the C dependencies. The idea is that even though they come out a little big, they are completely self-contained containers, which is kind of the purpose in the first place. So I can spin up a front end and without having to worry about what it might depend on, as long as it is just the basic stuff, which is just a broker and database. So yes, we tend to build our containers a little bit big so that they are as self-sufficient as possible.
Okay. Thank you, Rosario, for this.
Thank you. Thank you.